Hey, so today we're going to be talking about basically just showing some examples of optimizing the operation or maybe the sizing of a battery energy storage system, just a stationary battery that's sitting around. Not necessarily the most realistic problems today, but problems that are meant to kind of showcase some of the behavior of the optimization tools that we've been talking about using for the last few lectures. And we will talk about a fair number of the objectives that came up in the last couple of lectures. Things like arbitraging energy prices, meaning a buy low, sell high kind of thing with respect to a time varying price. So we'll begin with some examples. We'll show a little bit of code today about what programming a battery type problem would look like in CVX or CVX Pi. Won't give examples of other DERs, but just as a reminder, a lot of the DERs that we studied throughout the early kind of half of the semester can be cast into a model that looks very similar to the kind of battery kind of standard model. So basically the tools and the syntax and the coding and stuff that we'll talk about today is applicable more broadly than just to battery systems. We'll talk about what happens when you have non-monotone objectives, meaning if your cost function that you're trying to minimize is not, like, say, just a strictly increasing function of the variables in your problem, how to deal with that in battery problems. And then we'll talk about joint sizing and operation. This basically means if you want to decide not just how to operate a battery that already exists in, say, a building, but you want to decide how big of a battery should I put in. How would you formulate and solve that problem? Okay, so a few reminders about batteries. It's been a little while since we basically went through and studied all the kind of governing equations for the different DERs in the class. So this roughly, it's not the only way to model a battery, but it's a pretty good way, at least to get a fairly accurate model. So here, this is the discrete time model. This comes out of starting from the continuous time model and then solving it and so on. So this says that the new energy, so K here is the time index, so this is the energy at the next time step, is equal to a parameter A, where that is the exponential of the negative ratio here of the time step to the time constant, tau. And the time constant here is the self-dissipation time constant. So again, just to refresh your memory, if you leave your laptop unplugged or your phone unplugged or something like that for a long time before plugging it back in, eventually the battery depletes just kind of from its own sort of passive operation, even if it's not running any programs in the background or anything like that. So tau basically governs how quickly the battery depletes when it's just left untouched. Okay, so we have A times the old energy plus 1 minus A times the time constant tau times the chemical charging power that we put into or take out of the battery. And then there's a relationship between the chemical charging or discharging power and the electrical charging or discharging power. So whenever we convert sort of the flavor of energy from, say, mechanical to electrical or thermal or something like that, there's always, in general, an efficiency hit. And so here, if we are charging, meaning P is positive, then over here we would have the chemical charging power divided by the efficiency. So if we were putting 1 kilowatt of chemical power into the battery, and say our efficiency was 0.9, we would have about 1.1 kilowatts of electric power that we would need to pull from the power grid. And then conversely, if we're discharging, so say that we are dumping, say, a negative 1 kW, so we're getting 1 kW out of the battery electric, then over here we would only be getting, say, 0.9 chemical. Is that right? Anyway, this is the equation, and I'll show a graph of that in a sec. And then in general, we can also have some constraints both on the energy and on the power. So here, this is the energy constraint. It basically says we don't want the energy to go below some minimal threshold. This might be 20 to 40%, something like that, of the max. And then, of course, you can only put so much energy into a battery. Eventually, it maxes out. And then we have charging and discharging power constraints. So these are direct kind of constraints here on the electrical power. We can also write this in terms of the chemical power over here, and then we just have the efficiencies on either side. Okay, this is ringing some bells, I hope. So here's a picture of that relationship. So this is basically this function. I'm graphing it down here. So on the vertical axis here, we have what I call P in that equation. So that's the electrical power that we're pulling from the grid if it's positive, and then pushing to the grid if it is negative. And then on the x-axis here, we have the chemical power that's being stored in the battery. If we're charging, or if it's negative, that means that we're discharging. So we're moving energy from the battery. So the dashed line here would be a battery that had perfectly efficient charging and discharging. So if both of these efficiencies, A to D and A to C, were equal to 1, this would just be a line. It would, in fact, be a linear function rather than a piecewise linear function like this. And then the slopes here, we have the discharging efficiency here, and then 1 over the charging efficiencies here. So this is, let's see, the function made up by the orange and the blue curves here is this, what would be the curvature and the monotonicity properties for this guy? So convex, concave, or affine for curvature. Convex, yep, good. And then increasing, decreasing, increasing, yeah, good. Okay. So we can write that to convince yourself here. You can write that as the maximum of these two linear functions. So the orange line here is the linear function that describes the discharging, and then the blue line is the linear function that describes the charging. And if you take the higher of those two lines, you get this piecewise linear thing here. So that's where the max function comes in. Okay, so our dynamics here, we have a linear equality constraint. And then we have linear inequality constraints on both the energy and the power. And then this thing here that relates the chemical and the electrical charging power is a piecewise linear equation, right? Not an inequality. So we need to be a little bit careful when we program into something like CVX, this equation here. So let's first write down sort of a mathematical formulation of a simple battery charging discharging problem. And then in the next slide, we'll go through what the programming, sort of CVX formulation of that would look like for the same problem. Okay, so first, I think in optimization problems, it's a good idea to write down sort of what the decision variables are, what are the knobs that you're trying to twiddle, what are the actions that you can take. So here the variables are the trajectories of the energy, the chemical power, and the electrical power, at least in the way that I'm formulating it here. And of course, we talked in the early days of the optimization unit about how there are many different ways to represent problems. It's usually pretty easy to get an equivalent reformulation of a problem. And two problems, again, are equivalent if solving one means you can basically recover a solution to the other and vice versa. Okay. So then we write down the objective function. It could be minimize, could be maximize. In this case, let's write it as a minimization problem. So we take our price vector here, pi, which would have a vector of dimension k. You can tell it's dimension k because it's you're taking an inner product with it and this k-dimensional vector p here. So this basically says multiply the price at every time step times the electric power, and then multiply it by delta t, basically integrate it, and then add it up over the whole horizon. So this would be over the trajectory of time steps that we're looking at. K here, this would be the total cost of the energy that we're putting in or taking out of the battery. And then we have some constraints. So we have an initial state. So this basically says that the first element of this vector x, which represents the entire energy profile, is equal to some given number x naught. So this x naught here is a parameter in the problem. It's not a decision variable. So parameter means some data that, like, before you got to the optimization problem code, you would predefine it somewhere upstream of that in the code. So you would write down x naught is equal to 12 or something like that. Then we have our dynamics constraint. We have the equation that relates the electric power and the chemical power. We have our energy constraints, and we have our charging and discharging power constraints. And then these are all the parameters, basically. Anything that is not a variable that shows up anywhere in these equations, the objective function of the constraints, anything that's not one of these variables is a parameter. So we need to predefine these things. So we need the price vector, we need the time step, we need the initial state, we need this dynamics parameter A, which comes from actually the time step and the self-dissipation time constant, tau. We need the charging and discharging efficiencies. We need the limits on the energy and on the power. Okay, so what this looks like in CVX, we're just gonna like pretty much literally transcribe this statement into the CVX code. So here, we're gonna start by spelling out the variables. So we say variables x, and we specify the dimension of this. So this would be k plus 1 by 1. So this says that x basically is a column vector with k plus 1 elements in it. Pchem here, another column vector, but with k elements. and then P, the electric power, again, a k-dimensional vector. And then we want to minimize dt times the inner product of our price and our power. And that's just exactly what shows up here. And then we just write down our constraints. So here we have x1 is so the first element of x we constrain to be equal to x naught, the initial state. So there's a little bit of a weirdness between the mathematical formulation here, where the indexing I started at 0, and the sort of MATLAB code here, whereas MATLAB indexes things from 1 rather than from 0. So there's this kind of off by 1 shift between the math and the MATLAB. Python is a little different. Python indexes from 0, so maybe more convenient in that sense. I'll come back to this one in a sec. So this one, again, the P, this is basically just directly writing down this relationship that we see here. And then we have x min, x max. So this is basically a trajectory of energy constraints. And this is the full trajectory here of power constraints. So these, the second, the fourth, and the fifth constraints here are actually kind of vector-wise constraints. So this thing, basically, this is a vector of dimension k, runs from element 2 to k plus 1. This says for each element of this vector, it must be built between x min at the bottom and x max at the top. And then similarly, this pchem thing is a vector of dimension k. And so this basically says for each element of that, meaning at each time step, the power has to lie between these upper and lower limits. Yes, Grace.
Like it's clamping.
Yeah, so this is clamping the power, basically. It says, oh, you'd love to be able to charge it at 9 million kilowatts or something like that, but actually the wires are only so thick, so we can only put in 5 kilowatts. So it says basically don't go above that range. Yep. And then this is, again, this is like vectorized MATLAB code. You could write this with a for loop, a loop over k, and that would be fine within the CVX scope. But it's a little cleaner just to write it in this vector form. So here, this is actually k equations. There's a vector of dimension k over here. This is another vector of dimension k, and same thing with the chemical power. And so this basically specifies the dynamics that show up over here, but it specifies them for all time steps k. Yes?
Does that work in Python too, or would
does this work in Python 2, or would we need to do a loop? I don't know the answer to that question. I probably would start with a loop, and then I guess maybe play around with a sort of vectorized formulation. But MATLAB is like, so again, MATLAB we've talked about before. The mat in MATLAB doesn't actually stand for math, that stands for matrix. So MATLAB is like really optimized around kind of matrix and vector type calculations. So MATLAB code tends to be a lot faster if you can write it as an operation on a whole vector or a whole matrix, rather than sort of looping over all the indices. So that's just why I'm doing it here. For readability, probably I should have written this slide actually with for loop. It would be a little cleaner to understand. Okay, so so if you programmed it in this particular way, I guess, does anybody see a problem with this formulation as I've written it down here? Pretty much just like transcribe this model into CVX land. Okay, so if I program this and I say go, I run this chunk of code, I would get an error from CVX. It would beep on my computer and it would say, sorry, you have disobeyed the laws of convex optimization, and I can't solve whatever problem you've written down. Which again is not a certificate that the problem is not a convex optimization problem. It just says that it doesn't follow kind of the rule set of disciplined convex programming. So there aren't rules that sort of match, or that CVX knows that it can match the problem structure to. So does anyone see, if you had to look at this, if you were debugging your own code, which line here do you think would be the one that is causing the problem? Any guesses? So there's a hint down here. It's one of the constraints. Yep. So there are 5 to choose from. So which one of these do we think 1 through 5 might be an issue? One of the first 3. Okay, so we ruled out the bottom ones. It's probably not the top one, right? Yeah. Is get rid of that. Okay, so it's either this one or this one. And yeah, so this is saying one of the equality constraints right? Something that has convex on one side and affine on the other side with an equality in between is wrong. So yeah, it's the P1, right? Because on the left-hand side, we have just this is a very simple affine function of P. It's just picking out P. So it's the identity function, a very simple one. But on the right-hand side here, we have the max function. And again, that basically is this, if we looked at it just at one time step, which is not a linear or an affine function. It's a piecewise linear convex function. So here, CVX is complaining. It's saying, look, I don't know how to handle equality constraints where you're saying an affine function is equal to a convex function. In general, that breaks. Okay, so then here's a very simple example of the sorts of fiddly problems that come up when you're trying to do discipline, the convex program. And discipline means I have a rule set and you can't break the rules. And if you do break the rules, then it's on you, the modeler, to figure out what went wrong and how to reformulate your problem in a way that is friendly to the solvers. Okay. So we identified the problem here. It was this line. And in this case, there's a very simple fix, which is just to eliminate the electric power variables. So here we don't really need to specify both the chemical power and the electrical power, because if you have one of them, you can get the other one very easily by, again, just looking at this formula here. So the solution, or a solution to this problem, is just to delete this constraint. And P here only shows up in one other place in this whole optimization problem, which is in the objective function. So if we just take the left-hand side, sorry, the right-hand side of this equation and substitute it in for P, then we can delete P as a decision variable, and we get a convex problem. Okay, so now you can take this, you can copy and paste it into your computer if you want, and you can start getting solutions. So I'm going to show you some like very boring looking solutions to begin with, and then they'll get kind of progressively more interesting as we go. So in the first simulation here, suppose that we just had a constant energy price of about 15 cents a kilowatt hour, roughly what someone in a residential building would pay. And we begin with some energy in the battery, say 50% charge. Sorry, I'm showing here on the top the electricity price. It's just a line. It's constant, but in future plots that I'll show you, it'll be more interesting. Then here we have the electrical power that we're exchanging with the grid. And down here we have the chemical energy that's stored in the battery. And the dashed lines here are the lower limit and the upper limit. So here I think it's 13.5 kilowatt hours, roughly a Tesla Powerwall, something like that. And I'm saying, I don't know, 20 or 30%, whatever, that's the minimum energy. So the solution here, I'm saying I want to minimize the cost of energy from charging and discharging this battery, and I have these constraints. And you ask the optimization solver, what is the best thing to do? And it tells you basically dump the energy that you begin with and then do nothing forever, right? So it's super boring. It basically says, if you start my battery with some energy, fine, I'll sell it. But beyond that, I'm going to do nothing. I'm not going to use the battery. Okay, so very boring. We can get a little bit better. Also, this is a little bit unfair in some sense. So here we're optimizing over a one-day profile. And you can imagine saying, well, I don't just want the profile for today. I want a profile that I can implement day after day after day and have it sort of work consistently. So here we're starting with some energy, and then we're leaving the battery totally empty. So in some sense, we're leaving the thing worse than we found it. And you might say, well, we don't actually want to do that. So we can tune up this problem formulation basically by having a little bit better information or better specification of the problem that takes into account the fact that leaving some energy in the battery actually has some value to it. So one way to handle this would just be to say, look, you need to leave the battery in the final time step with whatever energy that you had when you began. So we could impose this as a constraint, or you could say you need to at least have as much as you began with. If you want to add more, that's fine too. So this is an inequality constraint there. So that's one option, would be to add constraints. And then another option would be to adjust the objective function to put in basically a price, a cost that values the energy that you end with in the battery. So here we're trying to minimize. So all this stuff, the positive stuff would be basically bad things that we're trying to make lower. And then anything negative is basically a good thing that we're trying to make better. So over here, we'd have some positive price, and we would subtract off of our cost. We would have a term that basically is like a revenue term that has to do with the value of the energy that we end with in the battery. And then this price here, what should it be? Well, I don't know. Maybe it should be the price that we pay for energy, or maybe it should be something else. I don't know. Maybe we assign a little bit of a higher price to it because there's some value for backup and resiliency and things like that of having more energy in the battery. And by the way, this doesn't have to be linear. It could be quadratic. You could say, I care about the final energy in a way that is not linear. It has some curvature to it. Okay, so here's what happens if we say the final energy has to be at least as big as the initial energy. Now we get maybe the most boring plot in the world. So it's just a bunch of constants. We do have this little sort of nub at the end here. And this is basically because we have this constraint that says the final energy has to be at least as big as the initial energy. And the battery that we're modeling has some self-dissipation. So even though we're doing very little here with the power, the energy is actually trending, it's too small to see, but it's trending slightly downward here. And then basically we put in some energy at the end in order to bring it back up to the initial energy. Okay, so basically this is telling you like if you have flat electricity prices, there's not much point in having a battery. You can't do a buy low, sell high thing. It's never low or high. Okay, so another way to do this would be, again, to add sort of this revenue term to adjust the cost function. Or to, basically, I guess, penalize having low energy at the final state. So here we get, with a very low price of 0.5, this is the price ratio between the final price and the price of electricity here, pi. So if we have a lower price at the end for the final energy than we have for the price of electricity during the day, then we do what you might expect. We basically, again, we dump the energy that's out of the battery and then we do nothing. We just keep it at the minimum. Okay, what if we increase the price? So now I'm going to show a bunch of plots here that look kind of similar. As we ratchet up the price, what happens to these profiles? So no action yet. Oh, and then between 96, a ratio of 96 or 97, we get a flip, basically between the sort of dump the battery and do nothing solution, and then the basically do nothing at all day solution. Okay, and then increase it a little bit. Okay, equal prices and so on. Still in the very boring sort of do nothing all day solution. And then whoop, when we go between 1.05 and 1.06, we again flip. And now we're in a solution where we're saying, basically, we're telling the optimization by the choice of pi tilde here, the final price. We're telling the optimization, look, I care more about having a final, a lot of energy stored in the battery at the end of the day. And it's saying, well, okay, if you really care about that, you really prioritize that, then I'm going to do what you want. I'm going to fill up the battery in the last few time steps here. And by the way, why does it fill up at the end rather than filling up in the middle of the day, for example? Any thoughts on that? What your answer was, it doesn't matter? It's an equal price all the time, but there is one thing that does make it matter, which is, did you have a thought? The dissipation of the battery, right? So if you were to fill up in the middle of the day, you would lose a little bit of that by the end. And so this is, even though it's I don't know what the self-dissipation is here, it's a very long time constant, so very low dissipation, but it's not zero. And the numerical optimization is precise enough to know, oh, okay, losing 0.01% energy would be bad. And so it charges at the end instead. Okay, and then we can keep raising the price a lot and we basically never change. So now I'm at 1.5, so 50% higher final price than initial. And we don't get any real change. We're ending basically with a full battery regardless. So here I am plotting on the x-axis the final price. This is basically just summarizing the results of those plots that I just showed. So this is pi tilde here. And then the vertical axis is chemical energy here. And this line, 0.15, this is the electricity price that we pay during the day. And this is the max energy, and this is the min energy that we allow. And then this is the initial energy, which I guess was whatever, 7 kilowatt hours roughly. Okay, so when the final price that we kind of manually tune is low, we get the sort of dump the energy solution here. So we end up, the final energy here, xk, we end up with basically the minimum allowable energy. And then there's this narrow range in the middle where the price pi tilde is similar to the price of electricity that we actually pay during the day. And during that range, we end just a little bit below the initial energy here. And this is the boring sort of everything's a flat line solution. And then if we raise the price out of that narrow range, we get, again, this kind of mode switch where, boom, now we're in the sort of fill up the battery all the way at the end of the day solution. So this kind of going to extremes behavior is really typical of linear optimization problems. So although, I'm going to go back a bunch of slides here, although our problem is technically nonlinear because we have a piecewise linear rather than linear objective function, CVX under the hood basically does some reformulations, get introduces a dummy variable to basically roughly linearize this nonlinear thing here. And so it converts this thing into the form of a linear program. And solutions to linear programs tend to be kind of at the extreme values of the feasible region. So they kind of go as far as they can in one direction. And so that's roughly what is happening here. It's kind of go to extremes thing. Okay. All right, so that was, what if we put in a price that values the energy at the end? Here's another option would be to impose a constraint, an equality constraint that says that the final energy has to equal the initial energy. And actually, we can delete the constraint that says we have some x naught, some pre-specified initial energy, and we can actually leave that as a variable and say you can choose, wherever you want to start in the battery, full or empty, but you have this constraint that you have to end sort of in the same position that you started in. Yeah, Zach, did you have a question?
So for the next day, like the 1.5 condition.
Going back here, yeah.
Would it kind of revert back to a similar thing for the one where it has the little tiny spike at the end to recharge the battery for the next day?
So if we ended this optimization and ran it again, but beginning with this energy state, so we go back here and start with an initial state of fully charged. You're asking kind of what would happen?
Yeah. Discharge again at the end? Or?
It's a good question. If I was a little bit more nimble, I would fire up the script that drew these plots and we could just do it in real time. But I'm not really prepared to do that right now. But I think it would depend on this ratio, right? It would depend on our choice of this pi tilde thing. But if we kept it as it is, my hunch, and we can verify this, but would be if we started it here, it probably would drift. It would let it drift a little bit, right? And then it would be down rather than 100% charge, at the t-1 point here, it would be 99.95% or something. And then it would do a little boop and refill it. So yeah, this would look like 0 with a blip at the end. I think we would go back to that solution. Yeah. That's what you were saying, right? Yeah. Yeah, I think that's right. Okay, so this is allowing the final and the initial energy to be free floating, but constraining them to be equal. So in this case, yeah, with a very boring flat price, you basically, if you start with higher energy, the self-dissipation will be higher because it's kind of, you lose energy in proportion to how much is stored in this model, at least. So here you want to start low because you don't lose as much. All right, so now let's change the price profile here. So what if rather than having a very boring 15 cents a kilowatt hour all day, what if we have a two-tiered time of use rate that says, look, the grid tends to be a little bit more strained in the afternoons and early evenings, so we'll give you a higher price at that time. So now we get a buy low, sell high kind of a thing. So here we are buying power pretty much at the maximum rate that we can in anticipation of this step change in the electricity price. So we fill up the battery, fill. The energy stored goes up until it reaches a maximum just before the price spike. And then boom, we go to discharging fully. So we dump that stored energy. And then I'm constraining here the final energy to be equal to the initial energy. So we can't dump basically below this level. And we end up in the same state that we began. So very intuitive, right? You don't need high-powered optimization tools to come up with behavior like this. You'd say, oh, my price is going to go up. Okay, well, then I better pre-charge the battery. Okay, what if we have a three-tiered energy price? Actually, it might be interesting in a future version of this class to not put in the profile here just to give you guys the prices and let you guess what you think the profile would look like. But again, pretty intuitive. It basically says, wait until the last minute, charge full blast such that you end up with a full battery just before the prices begin to go up. And then wait until the price is highest. And so the value of discharging the battery is at peak, and then dump the battery during that period. So again, very intuitive. You probably don't need optimization to figure something like this out. What about a real-time price? So here, this is just a simple sinusoidal price. We could just as well plug in say the MISO real-time prices from the grid operator in our region. But here we get, again, a kind of predictable behavior. So when the price is lowest during this trough, we fill the battery, and then we just kind of wait, hold on until the price is maximum, and then we dump during that period. Okay, and then what if instead of caring only about the energy, what if we also cared about something like the peak demand that we were putting onto the grid? So we'd say we want to take the maximum of this power signal that we have in the middle plot. So take the highest positive value of this thing and try to kind of compress that. So we basically now have two objectives. One is we want energy revenue basically from buy low, sell high kind of energy. And the other is we want a low peak. And so we basically balance those two competing objectives through this price pi d here, which would be a tunable price, again, that you could kind of fiddle with. And this would have a $1 per kW value. And I actually don't know what value I used here, maybe 10 or $15 a kilowatt. I don't know. Okay, so now we're still trying to, ideally, if we didn't have this peak demand term, we would wait until the electricity price was in this trough, and then we would charge full blast. But that would lead to a 5 kW peak. And so we actually want to lower that peak. And so here we basically spread out what used to be kind of, charging entirely during this trough here. We spread that out to charging throughout kind of many of the lower price, but not super duper low price periods. And then because we haven't here penalized the sort of negative peak, if you like, the trough value, I guess you could call it. Since we're not penalizing this, we don't get the same behavior on the discharge side. We just dump the battery full blast again. Okay. Questions about any of this so far? Okay. All right, so last time, actually the last two lectures, we talked about like 15 different objectives or something, a dozen different objectives. And so you could basically take the model that we have programmed here and you could start throwing in other objectives. You could balance multiple objectives. You could have 4 or 5 of them that you cared about. You could say, I want to track a reference signal. I want a low peak demand. I want to do buy low, sell high revenue, and 3 other things if you wanted to, right? And as long as your formulation is, done in the rules of corresponding to the rules of disciplined convex programming, you give it to this optimization tool, and it gives you back an answer. You may not be necessarily able to interpret the answer and the behavior quite as clearly as you can in these very simple problems, but the process basically is the same. And the code that I gave you early on in this section, you can modify fairly easily, basically by just adding objectives in that line that says minimize, right? So here, minimize dt times the center product, you just add some other terms up here. Okay, now let's make a small change to the energy arbitrage, the buy low, sell high problem. So let's take the same formulation that we had, but upstream of the CVX scope, let us just make one of the prices negative. So rather than 15 cents a kilowatt hour here, we get negative 15 cents a kilowatt hour. It basically says, I don't know, why would this happen? Maybe you had a ton of free wind power in a given location within the power grid, but all of the power lines were super congested. In order to basically, you couldn't get that wind power out of the area. So in that case, they might say, look, if wind and other generators in that area continue to produce power, it's going to cause problems on the grid. So we actually want to penalize generation of power. So the price might go negative. And that would send a signal to the wind farm, hey, you should turn off some turbines, curtail some turbines so that you don't get dinged with a penalty. And then the flip side of that on the demand side would say, normally we have to pay for energy that we use, but during these periods, it might be actually the opposite. We might pay you to use energy. And this actually does happen. So in some places in Texas, for example, you can find utilities that basically soak up wind that would otherwise be curtailed, and they will pay you to use it. All right, so if we do this, and we program it, we again get this error, disciplined convex programming error. But the hint or the explanation of what the error was is different this time. So now it says illegal affine combination of convex and or concave terms detected. Okay. So in this case, the debugging, like finding which line is the problem, is easier because this energy price, pi e, only shows up one place in the formulation, and that's in the objective function. So does anyone want to guess or explain why, with a negative price here, this leads to an error? Yep. Yep. Yeah, so we're trying to minimize this thing here as a convex function, but if you multiply a convex function by a negative number, it becomes concave. And so now we're trying to minimize a concave function, and that does not match the rules of convex programming. Sorry, I just need to grab a cough drop. Okay, so this is a reminder of what we saw last lecture at the end of the sort of objectives summary. So here we have this kind of compendium of the objectives that we might want to pursue: energy efficiency, energy cost savings, things like that. And we had curvature and monotonicity tags for each of these objectives. And so here we are trying to minimize energy cost, and we now have a negative price. So although the curvature of that function, it's a sort of a linear function of the power. Sorry, not quite. This would actually be convex in the case where we have the convex mapping between the electrical and the chemical power. But non-increasing is what we get here. So we used to be dealing with a convex non-decreasing function of a convex function. That's cool. But now we have a convex non-increasing function. And so we don't have a convexity rule that basically matches that. So that's why I've color-coded these things. These are objectives with which we need to be a little bit careful when we're programming. So for a battery problem, how would we deal with this? So suppose that you were in West Texas and there was tons of wind and you had negative prices sometimes and you wanted to be able to run your battery. Your job is to design code that makes the battery charge and discharge decisions for your company or something. And your code just breaks whenever there's a negative price. So your boss probably is not super happy. They say, well, what should I do for the next day? And you say, I don't know, boss, can't tell you. There's a negative price. Like I have no recommendation. So instead of doing that, there's actually a variety of ways. I will present two simple ways here. There are other ways, and I'll actually show you guys a recent paper from the research literature, which presents a third way and maybe a better way of doing this. But one fallback would basically be to assume that your battery has perfect charging and discharging efficiencies. So if your A to D and your A to C are both equal to 1, then back here in our piecewise linear convex non-decreasing function here, you would actually just be on the dotted line. And so you just get a linear function. And so then this problem kind of goes away. So that is one option. Now that's not a great option because you're now assuming that your battery is sort of better than it actually is, and that can cause problems potentially. Another option would be to basically split out the variables so that you have one corresponding to positive power that you're putting into the battery for charging, and another variable corresponding to negative power that we're taking out of the battery. So here we would split P into the charging component and the discharging component, and we restrict each of those to be non-negative. So now we're dealing with two variables, and then our dynamics here become a little bit simpler. We can write them in terms of the electrical powers rather than the chemical power. And so we have linear dynamics, and the objective function, I guess I'll show in a sec, but also basically becomes a linear function. And so we're back to kind of being okay. So let's look at the formulation for the perfect charging and discharging. Our variables here would be the energy and the power trajectories. We just want to minimize the linear function, the total cost of energy here. And then we have our constraint on the initial and the final states requiring them to be equal. And then we have our dynamics, our energy, and our power constraints. And the input data are basically the same. So this works, but again, it can cause some kind of weird problems. So I'm just looking at a very kind of, I don't know, unrealistic but very simple case here of the electricity price. So this is the same graph that I showed previously, just different kind of signals here. So here we have a negative price for a while, and then a step change to a positive price. So we're at negative 15 cents a kilowatt hour, and then up to 15, I guess. Okay, so now basically what the optimization decides to do, and here I'm optimizing with the somewhat unrealistic model, the perfect charging and discharging efficiencies. So here we basically fill up the battery, use as much power as we can while we're getting paid to use power. Why not? Then we assume the battery is full, and then we do nothing for a while, and then we have the step change here where the price goes up. We dump the battery, and then we basically do nothing at the end. So energy goes up as we're charging, comes down as we're discharging. That's all fine. Here, the black curve is the prediction, basically what we would expect if we had the perfectly efficient battery. And the dashed red line is the truth, what we actually get if we have an imperfectly efficient charging and discharging battery. Yes?
Why we don't see like a little blip right before the price jumps up from negative to positive, or why not make it take up the whole time since we're like dissipating a little bit? Like we were talking about the previous graphs, we have like that.
Mm-hmm. So yeah, let's think about this behavior a little bit more. So for example, why dump all the energy right away? Why not wait, or sorry, why fill up the battery right away? Why not wait a little while to fill up the battery over here? Yeah, so weirdly, we actually want dissipation. It's like everything, we're like in a bizarro negative world, right? So here you actually want to fill up the battery early so that you can get more of the self-dissipation to happen, because that allows you to buy a little bit more electricity later to refill for those losses, basically. So that I think is why we don't wait, we go hard right away here. Yeah, why don't we have a little blip here? I'm not sure about that one. Yeah. It might be there and just really small as possible. Yeah. Okay, so if we compare the prediction that we get from our efficiency equal to 1 model to the actual what we get with the not perfectly efficient model, we basically stop charging a little bit before we need to, because we think that we're putting energy in at 100% efficiency. We're actually putting it in at 95% efficiency, and so we end with a little bit of headroom left over in the battery that we're not taking advantage of. So we'd make a little bit less money basically during that period. But then when we begin discharging, two things are happening. One is we actually have less energy in the battery than we thought we did. Okay, so our starting point is actually lower. And the other is that we actually bleed more energy out of the battery than we thought we would as we're discharging. Because rather than discharging at 100% efficiency, it's only 95%. So we have to pull more chemical energy out of the battery to make that happen. And so for that reason, the measured energy in the battery goes down below the minimum allowable energy. So if whoever owns the battery always wants to keep 20% of energy in there just in case, now you have violated their directive, right? So this would not be a feasible profile, basically. Not huge issues, solvable issues probably, but yeah, something to be aware of. Okay, what does the problem formulation look like if we separate out the charging and the discharging powers into two different non-negative variables? So here we're choosing the energy profile, we're choosing the charging powers and the discharging powers, and we might as well just work with the electric power that we're exchanging with the grid rather than the chemical power. So the power P is just equal to the difference between charging and discharging. And we just, again, have all the same constraints. And our dynamics look a little bit different, but they're still kind of linear dynamics here. And then again, we have non-negativity constraints on both the charging and the discharging power. Okay. So again, we can get some weird behavior. Usually it only happens in kind of these pathological cases where you have negative prices and you're being encouraged to use energy, things like that. But nonetheless, I think it's important to understand when this model can fail or just lead to weird behavior. So I'm showing the same plots that I've shown before, and we have the same price profile that we did previously. So it's negative for a while. This is the utility saying, please soak up all this excess power that we have, and then it becomes positive. Okay. So then what is the strategy here? Oh, and by the way, here I'm using a very unrealistic, and in reality, charging and discharging efficiencies are only 50%. So we lose half of the energy that we pull from the grid when we store it in the battery. So this is not realistic. I'm just giving you guys some intuition for what can happen in these problems. All right, so what's happening here? Well, we again are basically charging the battery when we make money by charging. And we do that for a while here. So here the dashed blue line is the charging power, and the dashed orange line is the discharging power. So here we are charging full blast the entirety of this period. And then weirdly, we begin to actually discharge toward the end of this period as well. So we're simultaneously charging and discharging a battery. So with some types of energy storage, you can do that. For example, thermal energy storage, if you're just storing a bunch of hot water, you can both dump new hot water into the tank and also pull out stored hot water. That's fine. You can have pipes going in and pipes going out. But batteries typically only have kind of one pipe going in and out. And so you can't have current flowing both into the battery and out of the battery at the same time. So this is an unphysical type of behavior. And again, what is the impact of that behavior? Well, we think what is happening is we fill up the battery, we hold it full, and then we just dump all that stored energy. In truth here, we would be filling up the battery and continuing to fill it up. And then basically going above the stored energy, the maximum amount of stored energy. So this wouldn't really happen. Something else would happen in reality. We would clip or something like that. But anyway, so there's this mismatch between sort of the real model and the model that we're using for optimization. And then, so let's increase the efficiency here. So we went from 50% to 55%. And our simultaneous charging and discharging actually begins to happen earlier, and it happens at a higher level. And as we raise the efficiency, 65, 70, 75, 80, we basically do more and more of this simultaneous charging and discharging. And if we get up here to 95%, a realistic percent of efficiency, actually we'd be doing this simultaneous discharging and charging for hours and hours on end. So under the hood, what the optimization sees is an opportunity to use more energy by basically burning off energy. So it's using the fact that it can waste energy, right? It can dump waste heat. So it's dumping waste heat through charging and through discharging in order to basically have a full battery, but still continue using energy. And in that way, it makes more money, or it thinks it does, because it doesn't have a constraint that says, look, you can't charge and discharge at the same time. So again, this mostly happens in like weird cooked up examples. In reality, we don't have negative prices very often. It's becoming a little bit more common as we get more renewables and stuff on the grid, but again, these are kind of pathological cases, but just something to be aware of if, I don't know, you go to work for a battery company. And actually, before I jump into the last example, I'm just going to show you real quick the paper that I put up. So I just think this is kind of cool. First, this is a paper called "When Are Lossy Energy Storage Optimization Models Convex?" And it's written by a grad student from Cornell, currently a grad student, so probably at about the same year in their education that some of you guys are, and actually one of my former mentors from grad school. So I went to this university for my PhD. But this is a whole paper It's actually not yet published. So it's on what's called arXiv, the arXiv server, which is a place to basically put up preprints of your paper so that kind of puts your name, your stamp on the ideas that you have in case you're worried about someone scooping you. But also it makes your research publicly available sooner. Sometimes the publication process can take months or even years. So this is a way to get the ideas out more quickly. But so they write a whole paper that's really actually about this idea that, well, what if you have a lossy battery that has imperfect charging and discharging efficiencies and some self-dissipation, and you want to solve some problem. You want to do reference tracking, or you want to do price arbitrage, and the prices might get negative, things like that. And they are trying to basically sketch out conditions and algorithms that you can use to do that optimization. So they go through and they specify essentially the same model that we're using here. Notation looks a little bit different, but more or less the same thing. And they prove a couple of theorems that basically sketch out some other conditions or some other models that can be used in order to get essentially be able to use convex optimization software to get global solutions and polynomial time and things like that. So if you are interested in this, the trick of it, I won't go through all the details. It would take a little while to read, but I encourage you, if you want to just see a nicely written paper on a relevant topic that's actually completely current, it's not even yet published, you can check it out. But the big idea there basically is that it uses essentially elimination of variables. And we've been eliminating one of the power variables, and they basically do the same. And they write the cost actually as a function of the stored energy. There's an equation that relates the energy and the power, that's the dynamics. And so they kind of invert the dynamics equation to more or less eliminate the power and write the objective as a function of the energy only. So anyway, kind of cool paper. But. Okay. So now if we go back to our kind of compendium of objectives that we had here, another one that had no clear monotonicity properties was the reference tracking objective, so trying to minimize the error between a signal that you want to track and the actual measurement of your power. So let's think about that one. And I think for this one, I'm using the separate charging and discharging powers, the model that we just went through here. So now the objective, rather than sort of energy arbitrage alone, sort of buy low, sell high in the energy term, we want to do that, but we also want to be close. And here we're measuring distance in a 2-norm sense. So we want to be close in this kind of root mean squared error sense. We want to be close to the reference R. So we want our measured power to be close to that signal. So here, electricity price is in the top plot. Electrical power exchange with the grid is in the bottom. And then the stored energy in the battery is in the middle. And then the stored energy is on the bottom. And in the middle plot, now we have this additional trace, which is the reference signal R. So this is some wiggly thing that we're trying to track. And so ideally, if we perfectly did this objective, we would put the power, the black curve, directly on top of the red curve. And then this tunable price here, pi t, basically governs the trade-off between these two objectives. Right. So relatively low price here to 12 cents per watt. Let's start raising that, 13, 14. As we go, we basically get closer and closer to tracking the reference perfectly. And above some level, basically, we just get boring solutions. We basically just stay up there. Okay. And down here, in these plots, we again have the prediction made by the model that has the separate charging and discharging. And then we have the truth of how close we're tracking the reference here. With the more accurate model that doesn't allow simultaneous charging and discharging. And so in the bottom plot here, they're on top of each other. And all that really means is that in this case, for a reference tracking problem, even if we're using a kind of not exactly accurate model for optimization, we still get decisions that are perfectly fine. So the reason for that is there's no real incentive here to be both doing the charging and discharging at the same time and using this kind of fictitious way to burn off power, to waste power. So anyway, there's no incentive to waste power, so we're sort of fine with these relaxed models. So the upshot here is if you're doing something like frequency regulation type problem, probably using the model with the separate charging and discharging powers as decision variables would be fine. Okay, So the last thing we're going to talk about here is what you might call a more of a design problem. So deciding how big of a battery you'd want to put in, rather than thinking about strictly the optimization of the operation problem. But any question about the last two sections before we wrap up with this one? Yes, great.
So we don't have to say that it doesn't, can't charge and discharge at the same time? Because it doesn't get any incentive?
Yeah, so if there is no real incentive in your problem, like if there's nothing, no pathological thing like a negative energy price or something like that, that puts in place an incentive to basically burn off and waste power. So if you're in a problem that doesn't have something like that, in other words, most problems, then it's probably fine to separate out the charging and the discharging powers, rather than just having the one kind of power variable. Yeah. All right, so to kind of balance the operation and the sizing of a battery, we need to think a little bit about expenses that happen kind of once at the beginning of a project and recurring expenses that might happen over and over again throughout kind of the lifetime of a project. So to do that, this is something like a net present value calculation is what we're building up to. So if you've taken an engineering economics class, you've probably seen stuff like this before, but I'll go through it again just to be sure we're all kind of on the same page. So yeah, suppose we have to buy a battery up front, and we know that if we have a bigger battery, we're going to be able to do more with it, do more buy low, sell high, or something like that later. But we have to pay more up front for a bigger battery. So how do we kind of trade off between those current expenses and the recurring ongoing expenses? So the idea here is that, yeah, most people would prefer a reward now to a reward later. So $1,000 in your hand now versus 1,000 next year. You had $1,000 now. Well, I don't know, you could take it and put it into Bitcoin or something like that and have $1,070 a year from now. I don't know, or put it in the stock market right now. That might be, you might prefer money later to money now, I guess, since everything is tanking. But anyway, in general, people usually can turn money into more money. And most people have some number in their head. I don't know, if you talk to like an investment banker, they have some sense of, on average, year to year, how much they can increase a pile of money, right? Maybe it's 5%, maybe it's 10%. I don't know. Does anybody like play around with stocks and stuff? Yeah, cool. So do you have a number in your head, like how much I could probably make in a year from 8%? Yeah.
It depends.
Yeah.
What
What you're investing in, of course. Yeah. And if you get lucky or not, right? And yeah, if you hedge over many investments versus put it all into one thing, and right, it's complicated. Right? But anyway, so most people, decision makers around money, have some sense of this. I think typical stock market returns might be like in the 5 to 7% range, something like that. I don't know. Maybe higher if you're really, really good at it. So anyway, for that reason, you'd probably trade $1,000 now for $1,000 times some positive factor later. So if this row here is basically better than what you can make on your own through whatever investments you like to do, you might say, yeah, no, that it would save some hassle and whatnot. Sure, I'll go with that. Okay, so then economists basically use this to talk about the present value of money. So if we imagine that some amount of money M will arrive a year from now, then the present value, or the discounted value, is just that amount divided by this factor 1 plus rho. So divided by 1.05, 1.1, something like that. And then you can iterate this logic kind of forward through time. So if you have a cash flow that'll happen 2 years out, or 5 years, or 10 years, we again can kind of map that into a present value of money. So if Mn is the value of money that will arrive n years out, so 10 or 15, then we convert that to present value of money basically by dividing by, again, the same factor, 1 plus rho, but raised to the n power. So this allows us to basically do the kind of conversion, the balancing between future recurring costs and initial or capital costs. So suppose that we're going to do a project, maybe it's a battery project, maybe we're putting in a power plant, I don't know. It has some initial costs, C naught, to deploy. This could be $1,000 or $1 billion, who knows. It'll last n years, maybe 10 to 20 year range is typical for energy projects. And then it will have a net cost of C1 in year 1, all the way through Cn in year n. And these C's could be positive or negative. So I say cost just because when we frame convex optimization problems, we're usually talking about minimizing something. So cost is kind of a natural term, but you could just as well say value or revenue and think of these things as cash flows that would come in. It's a minus sign basically. And then project might have a salvage value in year end. So if you're putting in a big battery, you might use it for a while, its capacity might decay, eventually you'd be done with it, but you might say, look, we can tear it down and repurpose the cells for, I don't know, backup batteries for a factory or something like that. So you might get some fraction of the initial capital cost. C naught, you might get that back, 10%, 20%, something like that. You can sell it for scrap if nothing else. So then we combine all of these cash flows into what's called the net present cost, or the net present value if you're thinking about revenue. And it's just the initial cost plus the sum of all the discounted costs. So here we're only discounting the first cash flow a little bit by 5, 10%, but out here we might be discounting these end cash flows by quite a lot. Okay. And very often in modeling, usually not in reality, but as a way to kind of assess the kind of project finance metrics, you might assume that your annual costs are going to be roughly constant from year to year, basically to simplify your calculations. So you say, how much money can you make from buy low, sell high on a 1 megawatt hour battery? You might say, well, I don't know, 50K or 100K. Okay, and then just use that as sort of your year to year cash flow. Of course, you can get more sophisticated and just specify all the CI terms directly here. But in this special case where all the recurring costs are equal, then the net present cost actually simplifies somewhat. So we can eliminate basically all the C2 through Cn since they're the same as C1. And then we basically just factor out all the terms here by which we're discounting those cash flows. And so we can write that, the term in parentheses, to find a new variable and call it lambda. And it turns out that this thing is what's called a geometric series. If you think back to early calculus or something like that, I'm sure you wrote down or proved the sum of a geometric series. So you can actually write down in terms of the rho and n parameters what this lambda is. And then you'd still probably have the salvage value here discounted at rate n. All right, so that's sort of net present value stuff and discounted cash flow analysis in general, a very quick crash course. Let's apply it to a battery. So let's see, the initial cost of the battery we can model as either 0 if we have a really dumb non-existent battery. So we're not putting in a battery, the capacity is 0. Or let's model it as a linear function of the battery capacity, actually an affine function of the battery capacity. So this basically says, even if you put in a tiny battery with 0.01 capacity, you still need someone to go to the site. You have to negotiate a lease for the land. You have to bring in an electrician to do the wiring, right? You have to roll trucks out to the site to drop off hardware and stuff like that. So there's just kind of a fixed cost that happens if you choose to do a project. So that's the beta here. And then alpha is basically, once you've done that fixed cost, how does the overall project cost scale with the size of the battery? So this roughly is kind of like a materials cost for getting more lithium-ion cells or whatever. Okay. And yeah, I think this was for the Powerwall line. I don't know. I think these values are appropriate for something like a residential battery. They're probably much too high for a large-scale battery that you would see kind of at a power grid scale. And then let's also model the salvage value as just a fraction of the initial cost. So maybe you can only recover 20% or 30%, something like that, at the end of the project life. So we make this gamma 0.3, 0.2, somewhere in that range. Okay, so then we can do a little math and do some gymnastics and show that under these assumptions and with this model, in the case where we're actually putting in a battery, so the capacity is strictly positive, we can write out this term here. We have our lambda times our recurring annual cost or revenue. And then we have our initial cost here, which is following this affine model. And you can reformulate that a little bit, basically do some algebra, factor out the energy capacity, x bar, which shows up both in this term. And then the betas we can factor out and stuff like that. And then we have this new variable that we've defined pi x, which is a mixture of alpha. So this is the kind of slope at which the project cost scales with the size of the battery. And then it has also the discounting factor and other stuff in it. Okay. So then if we want to minimize the net present cost, taking into account both the initial capital cost of the battery, but also the revenue that we make from year to year, if we want to do that, well, we want to minimize this function over here. And this is all parameters. There are no variables in the problem, no x's or p's in here. So this thing is just a number that we can't influence by the choice of the battery capacity. So it drops out of the optimization, and we're just left with an affine function here, basically pi x plus this lambda times c. And c we will determine basically by optimization. Okay, so we're almost to the full problem formulation here. So let us, in addition, model the energy and power capacities here, the minimum energy that we allow as just being some fraction mu of the maximum. So this is like the safety margin that you want to leave in the battery just in case, could be 20%, something like that. And then let's assume that there's a fixed ratio between basically the energy capacity of the battery, the X bar in kilowatt hours, and the power capacity of the battery. So how quickly you can charge or discharge. So this might be somewhere in the range of 2 to 4 hours is kind of typical for lithium ion batteries. So we specify the mu and the nu. These become just parameters in the optimization problem. And then let's say the biggest battery you can buy, you can fit on the land that you have available, some E here. So this could be 100 kilowatt hours or something, the biggest you can fit in your basement. Okay, so then in our optimization problem, we want to choose the trajectory of the energy states. We want to choose also the trajectory of the power, the charging and discharging powers. And then we just throw in the size of the battery as an additional decision variable. And then our objective here is to minimize this thing. Again, this is just me expanding the formula down here. It's just expanding the C1 term to account for the sort of buying low, selling high that we're doing over the course of a profile, a power profile. So let's assume we're just going to optimize for 1 day. This is very simplistic, but let's assume we have the same kind of boundary conditions day after day after day, 365 days a year. So we'll just optimize over 1 day. So we'll set K such that it's a 24-hour horizon. And then we'll multiply by 365 in order to get the overall revenue that we would have in a year. And then this lambda term here came from our discounted cash flow analysis. And this really is what maps or basically balances the trade-off between recurring flows over n years at discount rate rho into kind of a present value of money. So here, this is the 1 day buy low, sell high revenue. We multiply it by 365 to get the annual buy low, sell high revenue. And then we multiply by gamma to basically get the present value of the lifetime of doing that year after year for n years. And then we have our constraints, dynamics, and so on, energy constraints, power constraints. And here I'm just using these formulas to simplify the energy and the power constraints. So this says you can't go below, say, 20% energy. And this basically just maps the energy capacity, X max, into the power capacities. So this says you can't go below your discharging capacity or above your charging capacity. And then we additionally say, okay, we're going to constrain this X to lie below the maximum value E. So you can't put in an infinitely big battery. You only have so many square feet to work with. Okay, questions about this formulation? Yes, great.
Do you go over, with the max of PChem?
Oh, this thing. So we already talked about this in some depth early on, and I know you came in a little bit late, so I'd encourage you to just go back. We only have like a minute left. But yeah, this is the mapping basically between the chemical power and the electrical power. So this whole thing here would be the electric power P. And there's some early slides that explain that. Yep. Okay. So what happens then? So this is the operating profile with a very low capacity cost, basically free battery. So we're paying for the labor, but you can get as big a battery as you want, and the cost is basically indifferent to that. We have electricity price in the top plot, kind of a time of use thing. Not very realistic, but just something to throw out there for illustration. We fill the battery, and then we dump it during the high price period. And the battery capacity here is actually, if you look at the axis, 130 or something like that kilowatt hours. So this is me basically saying that's the biggest value that you're allowed to put in based on the area that you have to work with. And so the solution here is basically saying, not only do we want to look for this power profile, which gives us this energy profile, but we also want the biggest battery that is available. Why not? It's free, right? Here's the other extreme. If we have a really a really high price for battery energy capacity, in that case, we get just basically no energy capacity. So the solution is telling us just don't put in a battery. It's not worth it. And if we had values of the price in between, we might get different looking solutions. But it turns out that actually we get this kind of mode switching behavior, this sort of going to extremes behavior in this problem, just like we did in the earlier problem in section 1. So here I'm plotting on the x-axis the price, the pi x, the basically the dollar per kWh price of putting in capacity. And then the top plot here is the optimal result. How much battery do we actually install? And so you can see that this is the max value that I put in, 135 or something. So as long as the price is below about $200 per kWh, we put in the biggest battery we can get. And then if the battery capacity goes above that, we mode switch down to basically installing nothing. It says not too expensive, forget about it. And then the net present cost with this big of a battery, being able to both do the sort of buy low, sell high thing over time, but also having to pay the initial cost. This is the net present value, the optimal net present value of the investment in this big battery. So we begin with a high $25,000 net present value with really cheap battery. I think I only did a few points in here is why it looks like a kind of step function rather than a smooth thing. But this would decrease more or less linearly. So we have lower net present value if the price of a battery is higher. And then eventually we're not doing anything. It's very, very boring. So we get 0 basically forever. Okay, so this again is not the world's most exciting battery problem, but I'm trying to just give you guys some tools and some intuition that if you're doing battery stuff in your projects or other DER stuff with thermal storage or using the thermal mass of a building or water heating or something like that, that you can basically take the code and the examples that we went through today, modify them a little bit for your problem, and you should be able to get some interesting looking results. So any questions before we wrap today? Okay, so just a last plug, you guys should be meeting with your teams regularly. You should be moving forward on your projects, really getting into crunch time on the projects. So don't let them slide. Okay. All right, thanks everybody, and I'll see you on Tuesday.